Hey guys, hello everyone. Welcome to the SN1 all of you once again. So this video is a continuation of the previous video where we have discussed the SN1 and SN2 reaction. Alright, of the SN2 reaction we have discussed, that is the mechanism, the factors affecting the rate of reaction and many other important points. So similarly, we are going to do the analysis of SN1 reaction as well. These are the basic reaction mechanism that we need to know, and after knowing the basic we move onwards to some examples from Jerry March. And some most of these examples have been asked in the CSR net question paper and in the other similar exam question paper directly, so we are going to go through all of these important examples as well. So let's start, guys. What is the SN1 reaction first of all? All right, so it is very very simple. First thing, what we would expect, since we have first understood the SN2 reaction, that fine, a primary alkyl halide is going to undergo a faster reaction with a better nucleophile, right? But look over here, it's a tertiary alkyl halide and it is bulky in nature. So if we were thinking on the same lines of SN2, agar SN2 hota yahan pe, then what would happen? The water attack will be hindered and the reaction should have been slow, but yahan aisa nahi ho raha hai. It is a tertiary halide, all right, it is bulky also, but the reaction is surprisingly fast. That means it is adopting a different mechanism from the SN2 mechanism. ये SN2 mechanism नहीं है, not the backside attack. The water is attacking in a different way and it is also a fast reaction. So how does it go? How does it form the tertiary alcohol, that also in a fast manner, even if it is bulky? Let's understand that. Experimental evidences for mechanism of an SN1 reaction. There are many experimental evidences that we are going to see. First thing, it is very simple. The rate law has been found out experimentally, and we see that doubling the concentration of the alkyl halide, that doubles the concentration, doubles the rate of reaction. Okay, but changing the concentration of the nucleophile has no effect on the rate. That means that the nucleophile, if it is not affecting the rate of the reaction, then it is not included in the rate law. So we don't include the nucleophile in the rate law, we only include the alkyl halide, which is our substrate in the rate equation. Okay, so what do we see over here? The reaction between 2-bromo-2-methyl propane, this particular molecule, and water, is it the one that we did in the previous example, and water is a SN1 reaction where S stands for substitution nucleophilic and it is unimolecular, just like SN2 reaction. In the previous video we discussed SN2. So what is this 2 for? That is bimolecular, all right, and here the SN1 is unimolecular. All right, so what is the difference? Unimolecular means that only one molecule is involved in the rate determining step of the reaction. Bimolecular means that there are two molecules involved in the rate determining step of the reaction. Who is the rate determining step? The slowest step, basically. All right, because a slow step has a very high activation energy, so उसी पे सब कुछ डिपेंड है कि भाई ये आगे जाएगा तभी रिएक्शन होगा. That's why it is the rate determining step. All right, so we move onwards and we see, let's say we are taking another example where we have taken a bulky molecule. Once again, it is a tertiary alkyl bromide, and the solvent is also not so small. It is a methanol molecule which is having a bigger size than water at least. So the solvent is nucleophile, so we can call it a solvolysis reaction as well. So that is going to give you the product like this, and the Br is substituted by the methoxy, and this is how Br minus eliminates. All right. Now this is a different reaction. The mechanism for SN1 reaction is also based on the following experimental evidences. The first thing that we see is the rate law shows that the rate of reaction depends only on the concentration of alkyl halide. Okay, this we have already discussed in the previous one. Second is the tertiary alkyl halides undergo SN1 solvolysis reaction with poor nucleophiles such as water and alcohols, but methyl halides, which are smaller ones actually, and primary alkyl halides do not. So this is a big revelation. That is, we thought that maybe SN2 reaction is going to be fast, right? But the smaller ones, the methyl halide and primary alkyl halide, they are not undergoing solvolysis. But the tertiary or the bulky alkyl halides, they are doing it really fast, and that also with poor nucleophiles as water. Water does not have a negative charge, it is just H2O. And ethanol, again, the lone pair. So, yes, thus methyl halides and primary alkyl halides and secondary alkyl halides only undergo SN2 reaction. So, the smaller ones will undergo SN2 and the bigger ones will undergo SN1 reaction, hence proved. Also, the substitution reaction of an alkyl halide in which halogen is bonded to an asymmetric center forms two stereoisomers. So in the SN2 reaction, we only had inversion, but here it is giving you two stereoisomers. That is, one with the same relative configuration and the other one with inverted configuration. This is a big revelation once again, that it is a different type of mechanism. Okay. We see that the mechanism for SN1 reaction goes like this. That is, first of all, if again we are considering the 3-degree alkyl halide, all right, we will say that the first step is the slow step. Or ये जो slow step है, what is this? Just the carbon and bromine bond breaks over here, right? This is the first step. Fine. That is a slow step because it has a very high activation energy. You see that the first curve over here, it is the rate determining step because it has a very high activation energy as compared to the other steps. Okay. So it is difficult to break the CBr bond by itself only under the influence of the solvent molecules. And then when the carbocation is formed like this, then the water is going to attack on a full-fledged positive charge. Since it is a full-fledged positive charge, even poor nucleophiles like water, they are going to add to the carbocation like this. Okay, so this is going to be a fast step, and that's why only has very little activation energy, only this much, right? So usually SN1 reaction is going to constitute of two steps, and the two steps are going to end over here only. But here in this mechanism, it is shown that when water is attacking one of the excess proton is also going to be taken away by the solvent molecule. After that, you are going to get this step. So the solvent exchange, the proton exchange is also always fast. So this last step is the proton exchange that you are getting. Okay, fine. But usually we write the graph to be like this in the SN1 mechanism. That is, you are having one step with a very high activation energy and the other step with a very low activation energy. Just that. Okay. Slide we talk about the stereochemical aspects of the tertiary halide. All right, so we have this tertiary alkyl halide over here, right? And we want to see that how it is reacting. So in a simple SN1 mechanism, and it is also a proof of evidence of SN1 mechanism, that is, it is going to give you two different products, right? So what happens is the Br minus is it is going to get eliminated, all right, and you get a carbocation like this. Now the carbocation is planar in nature. You know that a carbocation is planar. So whether the attack is taking place from above or from below, that is going to give you two different products. All right. So that's why, that is how one of the products, see, in one of the products, the OH minus has added on the same side as where there was Br minus, right? And the other product has OH minus on the exact opposite side of the carbon, of the Br. So this is the inversion product, and this is the uh, uh, you know retention product, you can say. So what is happening, one retention, one inversion product, since the carbocation is exactly having the same steric distribution on both the planes, so that is why 50-50% you are going to get both the products. All right, so we can now understand why SN1 reaction of a tertiary alkyl halide in which the leaving group is attached to an asymmetric center forms two stereoisomers rather than just to the inversion product, which was happening in the SN1 reaction. Okay, so thus the product is always a pair of enantiomers, because obviously retention and inversion product will give you two mirror images which are enantiomers only if these three groups are all different. All right, so let's say here we have R dash, R and R double dash, which makes this carbon an asymmetric center just like this, and that's why we are going to get two products. The one with the inverted configuration, all right, where the Br is on the opposite side as the OH, and here on the other product the OH is on the same side as the Br. So this is the retention product. So these are the basic things that we know. We kind of have an idea about the SN1 reaction. Let's move onwards. Now we will do a little bit of comparison between the SN1 and the SN2 reaction. So first we had seen the SN2 reaction. Even though the name is SN2, substitution nucleophilic bimolecular. Bimolecular means that the rate determining step has two species involved. One of them is the nucleophile and the other one is your substrate, the alkyl halide. But here in the SN1, it is unimolecular rate determining step, that is only one molecule is involved, that is the substrate. Second thing is, it is a one-step mechanism because the direct backside attack is taking place. All right, and SN1 is a two-step mechanism with a carbocation intermediate. You don't get any intermediate in the SN2 reaction, right? Next is rate decreases with increasing steric hindrance, because 1 degree, or let's say a primary alkyl halide, will give you a faster reaction compared to secondary and tertiary, and it is just the opposite for SN1, because now we know SN1 goes through the stability of the carbocation, which is written over here. Product has inverted configuration relative to that of reactant, and in SN1 we have both the retention and the inverted product, which is almost 50-50. Leaving group ability, guys, leaving group ability is again going to be dependent on solvent, so always take care of this. It's going to be like this: I minus, Br minus, Cl minus, and F minus. The same works over here as well. So that's why in the solvolysis reaction, if we don't mention what is the mechanism, then also it's fine. You just have to know who is the nucleophile, who is the leaving group. Alkyl halide reactants, methyl primary, secondary, these are more favored. Alkyl halide reactants, tertiary group is more favored in the SN1. The better the nucleophile, the faster the rate of reaction in the case of SN2, because the rate is proportional to both the concentration of the substrate as well as the nucleophile over here. But here the rate is only dependent on the concentration of substrate, does not affect. All right, so the strength of the nucleophile does not affect the rate of reaction. We have some really important examples to understand. These have also been asked in some of the previous years. First example is, if we see that we are having a benzyl chloride, and that also paramethoxybenzyl chloride, how it is going to undergo the reaction, which mechanism will be followed, SN1 and SN2, and how fast or slow it is going to be in comparison to the other molecules. So for example, let's also understand this with this example. Let's say we are having a benzyl chloride, a simple benzyl chloride we have, and then we have a paramethoxy and a paranitro. So what is going to be the order of reaction, right? See, if we consider the SN1 mechanism, electron donation favors the SN1 mechanism. Let's see. Now what happens is, here if the Cl minus leaves, you are going to have a benzylic carbocation on this particular carbon over here, and then the methoxy is going to donate the electrons, so it is going to be stable through SN1. That's why SN1 takes place. On the other hand, if we take an electron withdrawing group such as a nitro group within the benzylic compound, that will decrease the rate of SN1 reaction, because now if the Cl minus leaves, you are not going to stabilize the carbocation, it's going to be destabilized. So the same benzylic chloride instead reacts by the SN2 mechanism. Yeah, so definitely on the same substrate molecule, just by the change of a little bit of groups, right, functional group, you can have different type of mechanism. Since it is a benzylic and a primary carbon, nucleophilic substitution by SN2 also works over here. And for a simple benzylic chloride, it is still going to be SN1 because the benzene will stabilize through resonance. Now, what is the order of reaction? The order of reaction, if we consider, is going to be better for this one, for the paramethoxy, as compared to this and as compared to this. Now guys, here you see a complete comparison of all of the important or the compounds that we usually see, and these are the relative rate of reactions. All right, most of these are SN2 and SN1 reactions, so let's see what is important. Now, the rate of solvolysis, there are many questions in CSIR net which are asked on the solvolysis reaction. So, rate of solvolysis of the alkyl chloride in 50% of aqueous ethanol at 44 degrees centigrade. All right, fine. First of all, now if we have taken the allylic chloride to be 1, that is the relative rate we are talking about. So, we have to consider some of it, any one of it as a standard 1 value. So if the allylic chloride we are taking as 1, this is going to be considerably fast because you know that it is going to generate a allylic carbocation, and the allylic carbocation is going to be stabilized by resonance. So this is relatively fast. So let's see the other molecules. So the first one is going to be slower than the allylic chloride, you know, because there is only the stabilization is only through hyperconjugation, which is not a very good idea as compared to resonance. So it is a simple SN2 reaction and not SN1. All right, so it is slower. What about the next? It is a secondary alkyl chloride. So secondary chloride can do SN1 but mostly SN2, and that's why very slow. Third one, it is going to be a bit faster. Yes, much faster, because the tertiary chloride is very good at SN1 because it is going to form a very stable carbocation having 9 hyperconjugation structures. Okay, so look at the change. It is 21,000 from the isopropyl chloride just by increasing one more methyl over this carbon center. Very well, guys. Beautiful. Now, moving onwards, we see that we have another allylic chloride. Now, this is an allylic chloride once again. Allylic, yeah. But if we remove the Cl minus from here, it is going to give you let's say allylic carbocation. But how it is different from this first one? This is different from the first one, the first allylic chloride, because the rates are different. It is 1.0, it is 91. Why is that so? Because on the other side, when we are doing resonance, see what is the difference over here? When we are doing resonance from this side, you are actually getting the same carbocation, but this is also primary. Both the sides, it is primary. If you remove from here, you are going to get on one side, you are going to get secondary carbocation. That's why it is stable. Moving onwards to secondary to tertiary allylic al all right, guys. So yeah, basically what are we talking about is the Cl minus. If it leaves from here, this one, this particular Cl minus, then it is going to give you tertiary carbocation at one end. All right, that is this one. This carbon is going to become a tertiary carbocation after the Cl minus leaves and after resonance. So this is the best case where we are having 13,000 times faster reaction as compared to a simple allylic chloride, and overall this is the fastest. So allylic cation is tertiary at one end, and absolutely it is going via the SN1 mechanism. It is not SN2. Similarly, this chloride, if it removes from here, then it is going to give you a primary and benzylic and allylic carbocation. So it is 7,700 times faster than this one. So there are a variety of examples that we have. Beautiful comparison done over here so that you know that how much these factors are going to affect the rate of reaction. Now we are going to discuss some really important examples from Jerry March. And guys, these examples are the direct examples which are being asked in the examination. These are very beautiful example. You'll see why the application of SN1 SN2 is important. So first thing we are going to discuss about Walden inversion. I hope that all of you have heard about this. It is the same thing that we talk about when we are doing an SN2 reaction. Okay. Walden inversion is just like flipping of an umbrella. For example, if this is your umbrella like this, in this way, all right, and when strong wind passes by, the umbrella is going to flip like this, in this way, basically. All right, so that is the Walden inversion which is taking place in the stereochemistry inversion, right? So yes, this example is from Jerry March. Now at this point, see, Walden presented a number of examples in which inversion must have taken place. For example, plus malic acid, which is this one, it is a plus malic acid. How do we know plus or minus? That is experimental. This could be converted to plus chlorosuccinic acid by thionyl chloride SOCl2 and minus chlorosuccinic acid by phosphorus pentachloride. So do you see the beauty of this the utilization, the application? That is, I know I have this plus malic acid over here and I want to convert this into a chlorosuccinic acid in this way, and it depends on which reagent I take, the mechanism will change. So while we are using SOCl2, we are getting the SNI mechanism, that is substitution nucleophilic internal. It is a new, it's a different type of mechanism which is not seen for many molecules. For very few it is seen, and we will discuss that. Okay. So this one is going through SNI mechanism, and this is PCl3. If we are taking, it is simple inversion. So you see in the SNI mechanism there is retention. The OH is exactly on the right hand side and the Cl is also on the right hand side. So this is retention. This one is inversion. All right. So what is Walden inversion? It is just the flipping, or basically the inversion taking place while SN2 attack. Now, according to Walden inversion, we are going to see more examples, and look at this molecule, option number 3. Another example discovered by Walden is the formation of 3 from 4. Now, look at this. What is happening if you are taking a chlorosuccinic acid, 3 like this, and I once again want to convert the Cl to OH. In the previous one, we have converted from the OH to Cl, and now I want to move back and I want to convert this to the first compound. Now again, two possibilities. Either you are getting retention or you are getting inversion this time. Why we are getting inversion and retention? There are reasons. Now KOH, this is just simply giving you an SN2 reaction. That's why you have inversion and you've got the inversion OH. But in Ag2O, you are getting the same product. See, it is retention over here. Why is the retention taking place? This is a different concept known as NGP, neighboring group participation of the carboxylic acid. All right, which carboxylic acid? It is going to be the near one. Why? Because in the presence of moist silver oxide, it is going to create OH minus. Moist silver oxide, whenever it is mentioned, it is basic in nature, so it's going to have OH minus. That OH minus picks out this proton of the acid, and then it does NGP and removes this OH from here. All right, forms a three-membered ring, and then the attack takes place. We have a separate video for NGP. You can watch it over there. But it is very beautiful, has been asked plenty of times in the CSR exam. All right, further evidence or further important examples are, for the SN1 mechanism, if we try doing the SN1 reaction or the solvolysis of these different type of molecules, what is common in these molecules? All of these are strained, and all of these are having the leaving group on the bridgehead position. All of these, here the Cl minus is on the bridgehead position, that's going to leave a carbocation on the bridgehead position. Similarly, here there is a carbocation on the bridgehead position. If the Br minus leaves, it is going to again give you The carbocation on the bridgehead, the same with the triplet over here. If it leaves, it will give the carbocation on the bridgehead position. So all of these reactions are very slow. As an example, the number 11 example, this one, when it is boiled 21 hours with 30% potassium hydroxide in 80% ethanol, or 48 hours with aqueous ethanolic silver nitrate, gave no reaction in either case. It is not reacting. Why is it not reacting? Because SN2 attack to possible ही नहीं है. SN2 is a backside attack. You don't have a backside in a strained ring, right? Or SN1 is also very hindered because the carbocation which is formed will not be planar. If the ring is too small, then it will try to stretch out, and it cannot stretch out, it cannot become planar like this. But the ring is bigger. For example, example 12. The ring is a little bit bigger and more flexible. So, see, for example, the 2,2,2 bicyclic system undergo SN1 reaction much faster than the smaller bicyclic compounds. Uh, Although the reaction is still slower with the open chain reaction. So obviously the 12 is still going to be slower than a simple alkyl halide, but it is much faster than the first one, than 11th example, because of more flexibility and more planarity possible over here. Okay, so this is how you see different type of examples. This is how you compare. All right, and this carbocation, not only it forms, but it is also stable with this Lewis base at room temperature. All right, so this is what we have to consider. What are the physical properties, what are the chemical properties of these kind of molecules? Okay. Alright guys, so this particular example has been asked in their TFI examination, and this was taken directly from Jerry March. What is provided over here, that is, if just like the last one, we had a compound like this which had chlorine on the bridgehead carbon. But here, rather than chlorine, we have this chlorocarboxylate group on the bridgehead position, such that if the chloride decides to leave in this way, then there is going to be CO2 which is going to accompany it, and there is going to be formed a bridgehead carbocation. But the question is, if this reaction is impossible, how are we getting the products? It is not impossible, but you have to have a good nucleophile after the reaction. And let's say this is what you are going to get. There is a positive charge on the bridgehead position. Okay, but now the question is, the positive charge bridgehead position carbocation is so very unstable that it is going to take the readily available nucleophile, which is PHCl, that is chlorobenzene, which is a poor nucleophile actually, but it is also going to behave as a nucleophile because of the deficiency. All right, and along with that you eliminate CO2, BF3AgCl, and HF. Beautiful example of how SN1 can be done in strained molecules under some particular conditions. Okay, very very important. Now guys, there are many reactions of NGP which has to be considered while we are studying the SN1 and SN2 reaction, because without NGP it will not be complete, the discussion will not be complete, and that's why I have already made a separate video on NGP, like who can do the NGP, what is going to be the order of rate of reaction, and so many things. Alright, so you can watch it in the playlist of basic concepts NGP reactions. So now we talk about the SNI mechanism. This has been talked about a lot of times, but only a few compounds show the SNI mechanism. It is, as you can understand by the name, it is substitution nucleophilic internal, and part of the leaving group must be able to attack the substrate, detaching itself from the rest of the leaving group. So what do you understand? Let's see. See guys, there is a little correction over here. There is going to be an oxygen over here and no oxygen on this side. This is wrong. There is no oxygen over here. Only OSOCl. ठीक है. So it's going to be basically RO, all right, ROS double bond O and Cl. Okay, there is going to be somewhat like this. This one extra O will not be over here. Now the thing is that if the oxygen is exactly attached to the R group, then what happens? Then the O minus itself leaves. The O minus, SO and Cl, this is going to leave in the first step, just like this one. All right, and you are going to get an alkyl carbocation. Now this alkyl carbocation is so electron deficient, इसको क्या चाहिए? It requires some nucleophile. Where is the nucleophile? O minus? No. Now you know that SO2 can be eliminated, and along with that you are getting the RCl, that is you are getting the alkyl halide. अब ये SO2 क्या है guys? Planar तो बिल्कुल नहीं होगा. It is going to be like this. All right. Yes, it is not CO2. It is SO2. Now, yes, you are going to get this type of a molecule. इसको बोलते हैं SNI mechanism. And you say that why is it not changing the configuration? Because you'll say it is forming a intimate ion pair. That is, the two ions are coming together and they are not changing the configuration or anything moving around. They are sticking close, and the Cl minus is eliminated from your intimate ion pair. You say it. Now this is the most important slide of all, and this is where all the confusion is going to be cleared out about these kind of reactions. See guys, whenever you are given the simple alcohol, all right, and you have taken SOCl2, the alcohol is going to convert the SOCl2 into OSOCl. This is your functional group. All right, now there are various possibilities. If we don't provide anything else, then this path is going to be followed. That is, it is going to eliminate the oxygen coming from the alcohol in this way, and it forms the intimate ion pair where the Cl minus is going to attack over this particular carbon, all right, having the positive charge. Now this is known as the SNI mechanism या फिर substitution nucleophilic internal. This leads to retention of the product formation. Very good. Now let's move onwards. If I provided pyridine over here to the same mechanism, if I'm providing pyridine, then what happens is you are finally getting the inversion product through the formation of this sulfonium pyridinium ion like this. All right, it is interfering with the simple mechanism like this one. All right, ये मिलेगा यहाँ से, जिसकी वजह से क्या हो रहा है? You are getting inversion because the Cl minus is now free. The one Cl minus which was present over here, it is free to attack over this carbon, और ये इधर से निकल जाएगा. All right, it is giving you inversion. Similarly, when we are taking dioxirane, इसको क्या बोलते हैं? Dioxirane. When you are taking dioxirane, then also the whole SO2Cl group is going to be eliminated. All right, and you are getting the SN2 retention or displacement. ठीक है, retention of configuration in this way. So there are many fates of the sulfonium cation कि ये यहाँ से direct SNI mechanism भी दे सकता है या फिर SN2 mechanism भी दे सकता है, और third is it can also give you retention. Okay, SN1 SNI SN2 and SN2 like this. Fourth possibility, that is the addition of HCl will once again give you inversion. All right, so in only two cases retention, बाकी सब में inversion है depending on the mechanism. So there are going to be a lot more videos like this which are going to pop up really soon. Please inform me how you are liking this video, and also give a thumbs up, and also like and share with all of your friends. Thank you so much for watching.